One of the fellows of the University Research Center, and I am going to be introducing my speaker today. Dr. Robert Granger has a PhD in analytical and inorganic chemistry from Purdue University and serves as the Dean of the School of Liberal Arts and Sciences here at the University of Lynchburg. His research interests involve the synthesis of novel palladium and platinum-containing organometallic compounds used in both chemotherapy and catalysis. Today's talk will focus on a novel set of catalytic compounds that have been shown to mimic the processes of photosynthesis by producing organic molecules from carbon dioxide. Please welcome Dr. Granger.
Thank you very much, and thank you for being here, and I hope you're not skipping lunch on my behalf. Anyways, get started, and if you are skipping lunch, I'll try to be quick so you can get a little snack in. So anyways, the first question always is, why? Why do these sort of things? Other than trying to get tenure, there are actually good reasons. But reduction of CO2 is one of the first steps in photosynthesis. And for those of you who don't speak chemistry, reduction means you give an electron. During the process, oxygen is given off and organic materials produced, right? So sugar, cellulose, other biomass, but all that starts with photosynthesis. So it's inarguably one of the most important chemical processes that there is. The mechanism, in the textbooks anyways, I believe is wrong, and I'll show you why when we get to the end of this slide presentation. But anyway, oh yeah, there's my for the translation of chem speak into English. So this is a model of the catalytic center in chlorophyll. It has two iron sulfur cubane structures. Those are the catalytic centers that deliver the electron to the CO2. And the big protein that wraps around those, for the most part, is there as a structure to hold those two catalytic centers in close proximity to each other. And we'll explain why that's important in a little bit. But anyway, so that's, what's going on in nature is what we're on, right? And the idea here is two CO2s are reduced, so this little dot here is supposed to represent an extra electron that was given to the CO2. They snap together, and then the negative charges move out here to the oxygens, and you have this oxalated molecule. Why bother, right? Don't we have a lot of catalytic centers already in nature? That's true. The funding for this project was initially from NASA. It costs $25,000 a pound to put something into orbit. A typical oak tree is between 20,000 and 50,000 pounds, comes roughly to $500 million to $1.2 billion to launch an oak tree into orbit. Kind of silly thing to think about, but that's the why, because we want to have a way of cleaning air and producing useful organic materials. At least that's how we got the funding. I just wanted to understand the mechanism. But anyway, that's where that came from. I got started, strangely enough, not in this area at all. I was doing chemotherapeutic synthesis design. I was working with a microbiologist who was doing the cell culture work, and I was building cisplatin analogs. Cisplatin was the first organometallic chemotherapeutic drug licensed in the United States back in 1978. It was in Michigan. It's this simple molecule right here. This molecule and analogs where things over here have been modified is still widely used. Colon cancer, ovarian cancer, testicular cancer, bladder cancer, throat and neck cancer. It's a pretty common chemotherapeutic drug still today. Has horrible side effects, neuropathy being one of the most common ones. And another downfall of cisplatin is if you have a relapse in your cancer, it is almost always resistant to the cisplatin when you relapse. So the drug doesn't work the second time around. So a lot of research has been and is still ongoing in just modifying things over here. The goals are to reduce the symptoms and to reduce resistance to it. Right? And that's what I was doing. I was playing around with stuff over here. So this is just a little bit about cisplatin. I'm not going to get into this today, but it's in the slides in case there's anybody who wants to look that stuff up. It's free and stuff. Interesting, and it's got a deep, rich history. But here are some of the analogs that were being worked on. And I just want to point out this one here is different than the other three. If you're a chemist, you probably know that platinum in the 2+ state is square planar. Platinum in the 4+ state is octahedrally shaped. That's this one here. And so the one I was playing with was similar to this one. It's also interesting to note what's attached to the platinum over here is oxalate. That first step of photosynthesis, right? So it's just a weird coincidence. It's not really related to chemistry. But anyway, I was trying to make some of my molecules more water soluble, and I added this polar group here to a platinum 4 center. So it just gives it a little bit more polarity, makes it slightly more water soluble. And I synthesized this molecule in water. I purified it in anhydrous ether, and that's an important step. So it was purified in a rigorously dry system. And that was just pure dumb luck on my part. I would have never discovered this. But I went ahead and took its IR. This is an infrared spectrum. The only thing that's really important here is that I can see the ketone group. So I know that ketone group is there. I also got elemental microanalysis, which confirms the formula. So the formula was this. And then I went and got an X-ray crystal structure for those non-nerds in the room. That's sort of like getting a Polaroid snapshot. Shows the location of every atom in the molecule. And I got this. Now, that's where the ketone should be, but I don't have a ketone group there. I have a hydroxide right here, and a second oxygen bound there, and then attached directly to the platinum center. And what's interesting is I grew this crystal in a solvent called DMSO, and I just left it open to the atmosphere, and it was grabbing water out of the air. And it added water across that ketone. So this is a little easier to see. Here's the original molecule. Here's that ketone group. And this water here added across and made 2 hydroxides. Right? So there's the ketone, that water made those 2 hydroxides. That's called a gendiol. And then this hydrogen right there attached to that chlorine there, and spat off an HCl, and I ended up with that molecule. Back to this again. Now, I made the molecule in water, so I almost certainly made this initially. And then I just purified it in anhydrous ether and pulled the water off. That simply. It tells me that this water molecule can be attached and pulled off, and attached and pulled off. But not only is it attached, it ends up directly bound to the metal center, which means I can then deliver electrons or pull electrons off that small molecule using that metal center as a catalytic center. The actual step of events is I got the crystal structure back. And I'm like, well, that doesn't make sense, and put it on the shelf and was driving home. And when it hit me what I was looking at, I had to pull off the road and just stop and think for a while. I was like, oh, wait, that's actually significant. So the next question I asked is, well, can I add other small molecules across that ketone group? And well, first of all, I went and got the crystal structure of the hydrogen as well. So this is the 2 different versions of that molecule. The only difference is the water molecule between them. So here's the ketone group right there. It's the crystal structure of molecules. all this stuff down here is only important to nerds. It's bond angles and bond lengths and stuff, and we care about that deeply, but no one else does. So, on a Friday afternoon, I set up 4 vials, rigorously dried them with a flame, purged them with argon, injected them with anhydrous, acetonitrile is a solvent, it's kind of like phenol fluid. Put my compound in there and then bubbled carbon monoxide, carbon dioxide, hydrogen, and then just for shucks and grins, I put hydrogen in an olefin, which is something to do with double bonding. And then I went home for the weekend, came back on Monday, and they turned green. I was excited. So I cut the tops off, removed the solvents to try to characterize what I had made. And just by letting the solvent evaporate, it reverted back to the starting material. So kind of discouraging, but also encouraging at the same time. I can put these other small molecules on there and pop them right back off again. So went playing around with that. So here's the scheme that we were working. We put this into an electrolytic cell, catalytic cell, with electrode and some CO2. It's in a solvent. And the idea is our catalyst can pick up a CO2, adds across that double bond. Catalyst can pick up an electron from the electrode. The CO2 carries that electron away. It's a reduced radical, regenerating the catalyst, and then they can just repeat the whole process over and over again. Right? The first thing we did to test this, and I'm going to apologize, I'm going to have to show you an electrochemical scan and walk you through it, so for those who find this painful, this is called cyclophotometry. But it's kind of the key step in what's going on here. So let me describe this experiment. It's an electrode cell with 3 electrodes in it. One of the electrodes is pushing the electron on and off the catalytic center. The other 2 electrodes are there, just one is as a reference so you know where 0 is, and then the third one is the opposite of what's happening at the working electrode. And you scan negative first. So if you're looking along the axis here, the voltage is getting more and more negative, and I'm watching the current on this axis. So as the voltage is scanning negative, and we started right here, I see some current, right? That brown wave, I'm looking at the black line right now. And that first hump is the platinum center going from 4 plus to 2 plus. It's picking up 2 electrons. And then we kept scanning out, and we see another wave that's going from 2 plus to 0. Then we got to here, and we reversed the scan, and now we start going more positive. And as we go more positive, we pull 2 electrons off, 0 to 2 plus, and then I have to scan all the way out here to get back to 4 plus. Okay? You're thinking, wow, why do we care? The blue line is when I put CO2 in there. And what's 2 important things? I see a lot more current. That means that the CO2 is carrying that electron away and the platinum can pick up more electrons. And then the second important thing is I don't see a reoxidation wave over here. And the reason I don't see that reoxidation wave is because the CO2 carried off the electron and the platinum's already reoxidized, so it can't get reoxidized by the electron. So it's a real quick and dirty test to see if I should do more tests. This says, yeah, it seems to be working. Right? This whole experiment only takes about 25 minutes, so it's a good way of just doing a quick preliminary test. So we were very encouraged. We then went and got a bulk electrolysis cell, trying to see if we could make some more interesting materials. But let me talk about some of the challenges. And I'm compressing like about 12 years of work in a 25-minute talk here, so just FYI. Lots of people have been working on these sorts of problems. And when you reduce a CO2 radical, that's this right here, it has one of 2 fates in these sort of systems. It can bump into another CO2 radical bumps into a CO2, and the end products of that encounter is carbonate calcium carbonate is limestone, so that's not a particularly useful thing if you're on a space station. You don't really want to be making limestone. And carbon monoxide, which is toxic, it's also something we don't want to be producing in a closed environment. So that's not what we're going for. Also not what happens in trees and stuff, right? The other fate is two CO2 radicals can find each other. And you end up with oxalate. So that's what you're going for, equation 2. Most of the research in this field, you get equation 1. And the reason, and this is, who's had a Gen Chem class? Oh, excellent. All right, I can speak a little bit. So if you remember from Gen Chem 1, the rate of a reaction is a function of concentrations and the rate constant. And although the rate constant is very favorable for equation 2, the concentration of CO2 normal versus CO2 radical drives the forward reaction for equation 1. Right? It's just a matter of concentrations. The CO2 radical goes out into the world and is surrounded by regular CO2s and bangs into one of them first. Right? So that's the problem. So think back to the opening slide, second to opening slide, where I showed that model of chlorophyll. And I said that protein's main function is to hold those two catalytic centers close to space to each other. Right? The reason is you want to make two CO2s radicals in that little pocket between those two ferredoxin catalysts, so that the two CO2 radicals find each other before they find something else. Right? So the trick in a chemistry lab is, can we mimic that same process by getting two catalytic centers close together? And a lot of researchers have tethered different catalysts with organic linkers and stuff. But this system is a little different because it's ligand-based. And I have room to put another one of these DPK ligands on here. So this is another crystal structure of another molecule I made. And you can see I put two DPKs onto one platinum center. And in this picture, you can see both of them have split a water. So I got two waters across here too. That's a DPK with a water there and a DPK with a water there. So the idea is, well, if I can get two CO2s on there, I can make two CO2 radicals within the same solvation sphere and hopefully make oxalate. And the platinum family, nickel, palladium, platinum, likes to change oxidation states 2 electrons at a time. So everything's looking good. We made this molecule, went ahead and did some of the same experiments. Here's the IR, there's my ketone group, so I can show it and pull that water off. Another CV scan showing increased current when there's CO2 present. So looking promising. And then catalytic scheme looks just like the other one, except I'm picking up two CO2s, 2 electrons, 2 radicals being formed at the same time. So that's the goal. And then you want to make oxalate. Any questions yet? Questions really? All right, so here's the cell that I used to do a bulk electrolysis, try to make enough product to analyze it, see if I can find some oxalic acid in the end. For the nerds, I just got all the conditions of the reaction there, but not interesting really. And then we went looking for oxalate, right? So the solution for the bulk electrolysis, just have to give you one extra piece of information. I had to first treat it with ethyl iodide, convert. If I made any oxalate, it would be in the form of potassium oxalate. That's because the salt that was in the cell was a potassium salt. Something happened over here, but I was put ethyls here to here, so this becomes volatile. It needs to be volatile to be analyzed by GC mass spec, which was the tool we were using to look for this. And then we went ahead and took a GC scan. So again, something weird happened here. Well, that's got messed up. But anyway, that's oxalate. That's diethyl oxalate. and then some fragments that come from it. And then down here is a commercial sample of diethyl oxalate. So we found it, right? We were making oxalate, 2 CO2 radicals. So at this point, we were pretty happy. But then what happened next was a complete surprise. And again, I feel like I just keep getting the benefit of dumb luck quite often. Or maybe it's the benefit of being lazy. But the synthesis of this catalyst took about 3 to 4 days to make it. It's just a real tedious process. And so I was trying to come up with a faster way of making it. And I came up with this scheme down here on the bottom where I took my starting salt, platinum K2PtCl6, that platinum with 6 chlorines is just an octahedral kind of thing with platinum. And I reacted it with silver tartrate. For those who are chemists know that silver and chlorine, it's like the sledgehammer of pulling chlorines off of things. Silver chloride is insoluble in everything. And by reacting with a silver salt, I'm just stripping those chlorines off that platinum center and making it bare. But to stabilize it, I use tartrate, which is a 3- salt. It's similar to citric acid or other carboxylic acids in nature. But it will ball up around the platinum here, stabilize it long enough for me to put my ligand on it, right? So I'm thinking I got this one-pot synthesis, I can throw everything in, heat it up, filter off the silver chloride, I got my product, good to go. But something weird and wonderful happened. I didn't make this compound that I showed you on the previous slide. I made this. It's a polymer. It's DPKs with a platinum, oxygen chain running down the center. For the chemists in the room who are going, what the heck? Yes, that is a 4-coordinate oxygen. I need a P chemist to help me figure that one out. But it's like, there it is. Actually, this is a palladium center and not platinum. But these are the crystal structures. This is just different views, kind of looking down, the axis on this view over here. This is a counter ion that's stabilizing the salt. Here's another view of it in stick format. Just kind of see how it goes. The chemists are probably looking at these legs and like, well, that's still a double bond. That's a little longer than a single bond. But yeah, it's weird. It's weird. Shouldn't exist, but it does. And then I found in the literature there's a silver version of this similar molecule that someone had made a long time ago and postulated that this was the structure because it was pre-crystal structure days. Anyway, of course, the first thing I did when I figured out what we had here is run to the lab and try to see if we can make organic molecules from CO2. Did the bulk electrolysis again, and then we did some GC work, and I got these big molecules. And I looked at my student and I said, all right, you got some contaminants in there, that's not what you made. That looks like some plasticizers from a rubber hose or something. Go do it again. So these are phthalic esters. This is a phenolic material, some alcohols. Again, these look very organic-y, like you would maybe pull this out of some kind of oil or something. So there, she did it again. This time we got these molecules. Said, all right, still got a contaminant in there somewhere. Let's buy some new hexane and new everything and new hoses and clean the glassware extra clean and run to the third time, and we got these. So then we did, well, this is what is going on with your, I'm bringing them out. I'm bringing a thumb drive next time. Anyway, it's upside down and backwards. But these are some natural plant extracts. Benzoic acid that's what that was supposed to be. Salicylic acid is aspirin, and this is the phenol, but it's kind of all weird. Just showing you those materials that we're pulling out look very much like stuff you pull out of a plant. So we ran, don't do this. The first rule of giving a presentation is never put more than 10 words on a slide, right? I left this alone because I just wanted you to see, we tried to run every conceivable control to make sure that the materials we were seeing only happened when CO2 was present and the catalyst was present and electricity was being passed through the cell. And so we just ran all these different controls. And then the most significant control I ran is I went and spent $1,000 on a tiny little vial of carbon-13 labeled CO2, and blew that $1,000 in 3 minutes flat, bubbling it through my cell, and ran the catalyst for 3 minutes, pulled out a waxy material from the bottom. And how many people in here know what an NMR instrument is? Just a few. It's the chemist's version of an MRI machine. It looks at molecules instead of blown knees and things like that. But it relies on a nucleus that has a spin. And even numbered isotopes do not have a spin. Odd ones do. Most carbon in the world is carbon-12. And then a very small percentage is carbon-13. And so the NMR can see carbon-13. So that's why I was doing this, is I made some oily stuff in my cell and then analyzed it in NMR to see if the stuff I made was made of carbon-13. That would prove, without any doubt, that the material in my electrolytic cell came from CO2, right? And it worked. These big peaks over here are the carbon-13 peaks that went off scale after 16 scans. Normally in an NMR, you gotta run it for several hundred scans to see a peak. So, woo, it works. And before I jump into questions, if I get access to a lab again, my next thing I want to do is I would like to build a cell where I can pressurize and heat the cell, electrolytic cell, so that I can use as the solvent supercritical fluid CO2, and then repeat these electrochemical experiments using CO2 as the solvent, and that would allow me to create a lot of material at once. I've been doing this in a solvent called acetonitrile, and the solubility of CO2 and acetonitrile is very, very low. So I make very small quantities of this stuff at a time, and it makes it challenging to analyze. Anyways, I haven't done cancer research in a while because this has really got me gagged. The implications are huge. We're making phthalates, we're making phenols, we're making alcohols, and presumably, if I'm using this catalyst here, the only mechanism that makes sense to me is I make a whole lot of CO2 radicals, a whole bunch of them, all in close proximity to each other, and then a thermodynamic sync occurs, and I end up with these molecules. As opposed to the theory now that it goes through a sequence of very concerted steps that are highly controlled by the plant, right? It seems like it's just a thermodynamic process. And I do see bubbles swirling off the electrode when I turn the electricity on, so I assume that's oxygen coming off because I don't know where the oxygen is. But anyway, that's where I'm at with that. Back to the cool slide with the astronauts. Any questions? Yes.
How is it stability?
Stability of the catalyst or of the products we're making? The polymer is pretty stable. The one that's just a single metal center, I can usually let it run for about 15-20 minutes, and then I start to see metallic metal starting to form in the cell. So it doesn't have a super long lifetime. It goes probably through a couple thousand cycles and then it blows up. Probably can control that by not running the voltage too far negative. Figure out exactly where the sweet spot is and then holding it right there would be the way to make that work. I think if we took the polymer and embedded it in a mylar or some other plastic like that to stabilize it, you would make a more efficient system that way too. That would hold it together longer. Well, yeah, okay, in the back here.
So let's say you're successful, and would this be something you could like incorporate into paint on the space station, and it would scrub CO2 out of the air and make nice things instead of toxic things? Something like
It
that?
requires electricity, right? I mean, you are pumping electrons into it. And so my vision of it is a cell with a solar panel outside the station and the wire running in and running it that way. I would also think if you made a paint out of it, that then you would have weird stuff forming on your walls and oozing down, and that would be gross. I wouldn't do it that way. I would probably imagine you bubble the atmosphere through a cell and then harvest the materials on the other side. If the supercritical fluid CO2 idea pans out, you probably would just pressurize the air, expand it into a cell, and have it work that way. Or maybe you could embed it in a polymer, or in like a ceramic, porous ceramic, and push it through the porous ceramic. That might work too. Yes?
So I was going to take it to the next step, because I kept seeing reduction in CO2 and any implications for removing CO2 to mass scale in terms of climate issues.
I never approached this from an environmental perspective. And oftentimes people ask me the question from the title. They see the word reduction in the title and they imagine, oh, you're reducing it from the air. No, that's not what that means. It's chem speak for add an electron to. If I can find a different metal, it's possible. I don't think using platinum on a huge scale like that would ever be economically viable, just because platinum is very rare. I do have some slides I can show you that are after this one where I used copper and got some decent results using copper, which is cheaper, but it's also starting to become more precious than it used to be. It'd be really great if you could use something like iron and get it to work, or something similar. What's different about this approach to other organometallic catalysts is that the process is ligand driven instead of from the metal center. And so it's what we figured out, I've done some molecular modeling on this, is when the ligand binds to the metal, this is being the two rings, the two benzene rings, and my thumbs being the ketone, it bends it like this, and it puts strain on this bond, and it moves it closer to an sp3 hybridized bond angle, and so it wants to open up and grab onto something so that it can relieve that bond strain. And so that's what's driving the reaction. So I think you could probably find different metal centers and other ligands that are similar but have that same strain on the bond that causes it to run. Now that we understand what's causing it, we can seek out other ways of doing it less expensively. More economically. Yeah.
Now you said the part where you were getting those what look like pretty heterogeneous compounds. Is there any sort of like pattern to which ones you get? It look like you should just free trials to get different stuff.
Yeah, again, we're back to this thermodynamic soup idea where there's just a whole bunch of free radicals, and it probably has to do with how long we left it on, what the temperature was that day, atmospheric pressures. I think we just get a lot of stuff, and when we run the GC mass spec, there's a whole lot of peaks, and then you click into one of them, and it gives you this sample of what things you had. There was a long range of stuff all over the GC mass spec, and a wax left in the bottom that we never analyzed because it was too heavy to go into the GC mass spec. So I think we're just making a lot of different molecules. But I didn't play with it long enough. So the frustrating and challenging part of this is summer research with students. So we always get to the best part like 3 days before the summer process ends. Then you pack it all up for the winter and wait 9 months to play with it again. And then you pull it all out and try to get everything working again. So I would have loved to have ran the big cell a dozen more times and a couple more runs with carbon-14 CO2.
terms of any of that accumulating? So if you're gonna be running this over long periods of time, you said you would quite the accumulation.
Accumulation of.
Those products, so like if they were in your cell, you'd be running for an extended period of time.
Yeah, the cell's a little weaker, so I mean, I pull it out
So,
and then we pull stuff out. The other challenge is the supporting electrolyte that's in the cell also produces a lot of this other crud in there that you gotta isolate and clean, so you gotta do a lot of chromatography and stuff to clean it up. So there's just some basic qual scheme kind of stuff that you have to do. So, yeah.
You gone up the group and tried the nickel now?
I haven't done nickel, I've done palladium and platinum. Nickel compounds are notoriously toxic, and I was working with students, so I did. But if I had a glove box, I probably would have. I really wanted, my next goal right now is to work with an engineer to help me build an electrolytic cell that can pressurize it and run this in supercritical fluid conditions. I think that would be amazing, because I think I could probably make grams of product at a time and then really characterize the heck out of it. Yeah.
So what is your ultimate idea of like a sear, like a scrubber? Was it more atmospheric?
Scrubber. But the current scrubbers, you just pull the CO2 out and throw it away. This would be a scrubber that takes the CO2 out and converts it back into useful organic materials. So it recycles the CO2 instead of just removing it. Right? So you make oils and waxes and other things that you could then process into other materials. That's the idea. Basically, you make petroleum from CO2.
Push it to a refiner?
Hmm?
Push it to a refiner kind of thing?
I imagine submarines and space stations, but that's probably just because that's where I got my initial funding from. I haven't really thought about it beyond that. Yeah, I worked for NASA in grad school too, so we were doing CO2 reduction work in grad school as well. So this is something I've been dabbling in this arena for a long time. Anybody else got a question? Yeah.
So you had suggested the textbook version of photosynthesis is incorrect based upon what you've been doing. Can you explain where you think there's a misconnection?
Well, there's basically chlorophyll happens, oxalate's the first step, and then a concerted series of very highly controlled steps creates these molecules. I'm creating the same molecules from what I can't imagine any other mechanism but a free-for-all soup of free radical CO2s in a thermodynamic sink of just the most stable molecules wins. Well, it could be a kinetic sink, I suppose, but it's not I don't think it's a step-by-step, concerted, very controlled sequence of reactions that lead to these phthalate esters and phenols and ketone groups and such. It's just a soup of CO2 radicals. So I can now go back to that chlorophyll picture and imagine those molecules being produced there. Get all the way back up there. And this little pocket right here, look where this is being held in close proximity. If it's just spitting out a bunch of CO2 radicals in here, stuff's happening, and certain molecules are being made, but it's not a step-by-step reaction. That's my gut tells me that's right. I haven't proven it yet, but it'd be worth. Could be
Would
worth
the controlled nature be the physical structure of that molecule in the organism?
Of what the ultimate outcome is.
Well, right, in that array,
This
the
pocket.
chlorophylls are creating a three-dimensional structure that then provides for some control?
That's very likely, yeah. That you throw in a bunch of reagents and then based on the volume and shape of the pocket, you can only make certain things. That's kind of where I'm leaning, is that it's not as sequential as we think. Not as complicated as we had imagined. That from a chemical perspective, it's maybe a much simpler mechanism. Could be wrong. But it's my gut feeling right now. Anybody else? Yeah.
Could the structure and alignment of the pockets vary? Dr. Carlos?
Yeah, probably. I mean, that's the whole, how enzymes work, right? Is they have a certain shape and only certain molecules can fit in there. So, and most enzymes have an organometallic structure at the center of it that is the catalytic center. And the protein is there to create a pocket of only certain geometry. It only lets certain things in. I just think it's interesting that I'm making very similar molecules. Maybe what's different is chlorophyll pocket makes only a very narrow range of molecules, and then we have this with no pocket. There's no protein around it, right? And we're making a large array of materials, but they do have, they have a similar class, right? We're making phthalic ester, we're making benzaldehyde type things, and benzoic acid type things, and alcohols, which we also find in plants, right? Just maybe a larger array of them from a single catalyst, as opposed to a smaller, narrower band. Anybody else? All right, thanks for coming.